So the next speaker is Gabriel talking about wrapping the twisted for fans. That's the same.
Okay. So yes, I like. Do I have pointer?
The laser.
Yeah. Yeah. Yes. Okay. So today I talk about this award that that I had with these people here that I cannot show, but you can read. And like our starting point is our is start the theory, which is in equals to 4 super young males, and this is like a very interesting theory because it's a fourth dimension on a video cage theory, but it's also like amenable. It's possible to solve it for the many reasons. And today I will focus on like a baby theory of this theory, which is like curvy-folded version of an equal structure, and this theory is like less super symmetric, but because of that, it has a little bit more structure. So it has some twisted subaqua, which which has protected the dimensions, but they have non trivial functions, and this is what I am going to show you today how to compute. So, like, let's start. Like first, we have the setup. We have enables for super meals. I think most of you are like familiar to this, and I will focus today on single trace operators. So things like that. Uh, yeah, but and in this theory, you have two frameworks that are like successful, but of course not to the same extent. So you have the QSC, which is a machine to compute animal dimensions among some other things, and you have the hexagonalization framework for computing turbulent functions. Uh, which is in spirit kind of similar to TBA, but we don't know how to improve that to the level of QC or anything like this yet. And the basic idea is that you can compute a trivial function, which is a pair of pairs, uh, by like gluing two patches, which we call like hexagons, and we sum over all the possible numbers of virtual uh, particles living on the places that you cut, and integrate over the phase space, and uh, our English two theory is like obtained from some English two four theory by doing like an armfold projection, which is like just to take you start with SUK times n English for superior meals, and you perform a projection that breaks it into KSUN and this theory has equals to supersymmetry, and the projection is done like by this matrix gamma, which is just some phases on like each block of the SQNs, and what survivors of 10 equals to 4 field content are some adjoint scalars. So these are adjoint scalars of each SUN, and you have also some very fundamental scalars on the fundamental of one SUN and in the fundamental of the adjacent so on. And you have this for X's and this for us lines. I forgot to draw here, but you can like encapsulate a lot of these informations in a quiver diagram. And yeah, so like theory is known to be like integrable. This discussion was made like almost 20 years ago by like Weiser Sharaban and so many others. And as I said, it has the Chevapco is has protected dimensions, but nevertheless protected non-protected three state functions. And moreover, these structure constants were computed previously by localization. So we have something to compare to. And so the operators that I consider are these adjoint tobacco, which are made of these, and you can have an untwisted or twisted tobacco with some index alpha, which goes from 1 to k minus 1. And what we compute are treatment functions of this tobacco, and of course it can only be extremal because if you can only use z's and z bars, I guess it has to be extremal. And so this is what we want to compute. And the localization results take this form, this factorized form. So it's like roughly one factor per operator, and theses they are written in terms of some Fredholm determinants with some Bessel kernel that appears in like many other places in super conformal field theories, and as an example, it appears in the octagon, which is just the gluing of two hexagons along only one edge, and of course that makes sense that appears here, but it also appears in the subleading correction to the free energy in two theories. Yeah, it appears on many places, also in like Wilson Kelp competitions, and yeah. And okay.
What does extreme mean?
Extremal just means that one of the regions it's like zero, so you don't have any weak contractions like directly between these two. So yeah, so you see this length. Okay, so it's this property here that one of the lengths is the sum of the other two, and also these treatment functions they are only like cannot vanishing if alpha 3 is equal to alpha 1 plus alpha 2, because you need the conservation of also this number. So like first we were able to show that this has a much nicer form. This is a result we discovered, and the churches keep proved. And this is like a much more friendly to interoperability. So I will show you now how to compute this from interoperability. So the image that you should have 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 in mind is that you have a Turpin function like this, and you put a twist here, so that this twist is like alpha 2, this twist is alpha 1, and you see that this operator here has total twist alpha 1 plus alpha 2, and this has alpha 2, this has alpha 1. And okay, so the proposal is that you can still use the hexagonalization framework. The only difference is that you have to do like something to these magnums that are on these seams, these cuts that have two twists on it. Like help to now like any question? Okay, so I can continue. So I will just review some basic facts of this hexagonalization proposal. So like first of all, you have diagonals. They are always in a fundamental representation of SU trigonometry squared. So you can can write each diagonal as a linear chi a dot, where these magnums can have like four flavors, and I call them phi one, phi two, psi one, psi two, and for example, the fields each like exchange of fields is kind of represented by these magnums as in this way that I am showing. So you see that the scalars of n equals to 4, they are like written only with these phi's. You have the derivatives that are written with the only size, and you have still infernals that are written with the phi's and size. So okay, and you can move these magnums like along this hexagon form factor by doing some weak rotations. And yeah, but like maybe that's not super important that I explain everything about this right now. Okay, so like now that I explained what are magnums, I explain how to compute the hexagons. First of all, you need to move all magnums to the same edge, and you compute that as follows. You just split all the by fundamentals like that, and then the hexagon is roughly equal to the S matrices that you pick in splitting the magnums in this way. It's the S matrix times some scalar factor, and these hexagons, they have a property that if you have like like a hexagon with with rapidities on two virtual. Okay, so if you have an hexagon which had a magnum in this sim and one magnum here, you have a pole when the rapidity is coincide, and the residue of this pole is proportional to the hexagon without those poles. But this property is like very important because it means that in these integrals that I am showing you, you have to provide some prescription for how to regularize the tuples that appear, and this is crucial for our result. So okay. And now I just need to tell you how to twist this magnum. So I remind you the action of turbifold is something like that. Uh, Something like this here. And you see that this can be implemented in the magnums if you twist. You see, you need the x and the y to get the row, and the x bar and the y bar to get the inverse. So you basically need all the dotted the guys to be multiplied um, by one dot is multiplied by row, and by two dot is multiplied by row minus one. And so this is what you need to do. You in the scattering of these magnums, you need to pick some extra factors. And okay, and in principle, you could also include some twists. Like you can also deal with some other theories, like by doing some simple twists. But I note that our theory is particularly simple because the super trace of this twist is zero, and the anomalous dimensions will be will be proportional to the super trace of this matrix for tobacco. Uh, any questions? Okay. So our results, they are like basically this. First of all, we we noticed that the result factorizes in some pieces. So you have some pieces for when you take uh, the regularized part of when you have some magnons on bridges with the twists, and for each of the multiple insertions of magnons on each bridge, you get like this factor that I call B. This is just the determinant of our K. I will explain this later. So okay, so if you ignore all the poles in centigrade, this is all that you get. But now if you like pick uh, the poles that identify these two rapidities, you get some effect like this. WP. It suggests some contributions of these like effective wrapping magnums. Uh, that trickily, there are some contact terms that kind of renormalize the norm of the vacuum. And you also have these other kinds of poles that are some triple contact terms between three probabilities like this, and like remarkably, it contributes as with vector with the sum of all the twists and the sum of all the bridge lengths, some vector like this, and so this is B. This is what happens if you just like insert a bunch of magnums in one bridge and take some. You have something like this. For all therapy magnums, we were not able to fully prove this, but we checked in many others in K, like expanding the like both sides in K, and we were K, I mean, T matrix in powers of T matrix, and then we have this thing here, and when you put everything together, you have this result, which is exactly what I showed you before. That was the okay, just which is exactly what you had before from localization, and these results they can also be like related to some previous conjecture by like Benjamin, Alessandro, and Arthur, and so that's basically it. And what I did not show you today, but because I will not have time, but that was important. It's exactly how you like regularize the integrals to get all these different contact terms, and you can ask me in the questions. I can show you some extra slides. So the conclusion is just that we offered some evidence that hexagonalization can be like extended to orbitals of n equals to 4. A recent paper, also by Torben and Dennis, checked the opposite side, the two level triplet functions for excited states, and they also find an agreement with just weak contractions, and we also provided like a regularization procedure, which is like very physical. I can show you next slide. For computing treatment functions of twisted Tabaqua, in principle of in theory, but that's still to check. Like that's like something that it's in the future directions, which is how to resum this all of these contributions in a nice way for like when you have a non-trivial wave function, like that is when the animals dimensions they are not protected, and how can we use this simple time model of treatment function of aqua to like make some contact with QSC and the separation of variables. And this is work in the progress with the authors of the paper. And some other question that is left is we were motivated to look at this from the point of view of hexagons because the results from localization resembled a lot the kinds of things that you get when you glue hexagons. So some people expect that some integral structures would appear also in quiver theories, like away from these orbifold point. And these theories can also be tackled with calculation. So what we are doing now is to try to write the localization results for these more complicated theories in like some way that you make explicit some integrable structure or something like this. It's still not super clear what's the structure that will appear, and this is also some work in progress with me, some people in Desi and Shatmatsu. And this is it. Thank you very much.
Thank you very much. Any questions?
Yeah, you mentioned a few slides ago that you have these three different contributions.
Yes.
How does that compare to the theory that isn't twisted? Do you get the same three contributions appearing? Or
Okay, if you have tribute function of vacua in the theory that is not twisted, you don't have any
I see, these are all new.
of this. If you have a theory with excited statistics, but which is not twisted, you have all of this. But in our case, it's like much simpler than looking at excited states in the twisted theory, because immediately you have lots of complications when you can also have magnums on this part or this part or this part. So this is like just some simple setup to be able to understand how to regularize these integrals that appear and how to resum the result to like what's the structure that appear, and yeah, it was also useful to provide some evidence that you can extend the actualization framework for some other twisted theories that can be of interest for some people here that are trying to do some deformations of super immense.
How do you do localization in first dance of chess?
Okay, like the theory fold of this theory, it's just some quiver and constitute theory where all okay, so it's an constitute theory, and you have uh, the action of the matrix model that you get after localization computed by uh, Paston. Okay, so you are able to show that the a partition function for this like orbifold of n equals to 4, which is some n equals to theory, can be written as some matrix model with some matrices like labeled by the number of nodes in the quiver, and you have some action that depends on this A's, and this action is computed. It's like basically the same action for all these theories, and it was computed by Paston like how many years ago, and this is the starting point that many people in localization take to compute the partition functions and some other.
More? No. Let's thank Gabriel again.